In this video, we'll talk about aromatic hydrocarbons and functional groups, in particular alcohols and carboxylic acids. So aromatic hydrocarbons are going to contain a ring in which the pi electrons are delocalized throughout the ring. So the simplest case, and the only one we'll really talk about in this class, is going to be benzene. So if we draw benzene in a line angle structure, because of the position of these double bonds, we see that we can have a resonance structure where we can draw them between different carbons. And so this indicates that really it's a mixture of both. So the electrons that are making up those double bonds are really spread out through the whole molecule. This is often represented by them just drawing a circle in the middle to show that all those electrons in those double bonds are spread out on the ring. The formula for benzene then is going to be C6H6. And this is something that we commonly see for these aromatic hydrocarbons. When we're naming these, we're going to use benzene as the parent name. So in this case, we'd have benzene with a methyl substituent, so that's a methylbenzene. And if we have multiple substituents, then we'll state the location. As per usual, we will minimize the location numbers. So in this example, we have an ethyl group and a methyl group. Since ethyl is going to come alphabetically, we'll start there with the numbering. We'll number that 1. And then the shortest way to the second group, 2, 3, we end up with the 1-ethyl 3-methylbenzene. Certain combinations of atoms, when they're attached to these hydrocarbons, have sets of reactivities and properties, and they get special names. We'll call these combinations functional groups. And we can figure out a lot of things with the functional groups. One of the things that we'll be looking at a little bit later is using the idea of intermolecular forces to predict how functional groups are going to affect some of the properties that we observe. The first functional group we'll talk about are alcohols. The general formula for an alcohol looks something like this. The R that you'll see a lot in the representation of functional groups and organic molecules just means the rest of the molecule. So when we write it like this, we mean whatever attached to an OH somewhere, and that's going to be the alcohol, the OH. Some examples are this compound, so we have 2 carbons, and the second one's attached to an OH, or this compound right here where we have 1, 2, 3, 4 carbons, and this carbon right here is attached to the OH. These are both examples of alcohols, so something with an OH functional group. When we're naming alcohols, we're going to replace the E of the parent molecule with all instead. So if we look at this compound, if it was an alkane, this would just be ethane. And when we name the alcohol, it becomes ethanol. For this compound, again, we'd want to count the carbons. Since there are multiples, we want to minimize the position of the OH group. So if we start on this side, that gives us the OH at 2. And then we can name the position. So in this case, this would be 2 for the position of the alcohol group. And then instead of butane, we replace the E and make it all. So we end up with 2-butanol. If we have alkyl substituents, we are going to try and minimize location numbers. So in this case, that numbering system minimizes our positions. And so we end up with a 2-methyl, 4, and then 5 groups, pentanol. If we have a tie, then the OH group will take priority over the alkyl substituents. So in a case like this, we're going to prioritize the OH group. So with our 4 carbons in the chain, this would be 3-methyl, 2-butanol. For carboxylic acids, the functional group will have a double bonded O and an OH bound to a carbon. This H attached to the OH group at the end is going to be an acidic hydrogen. So these come off and give us weak acids. Here's a couple of examples of carboxylic acids. And when we're naming the carboxylic acids, this is similar to the alcohols, but we replace the E with oic and acid. We don't need to include the position of these because the acid is always going to be on a terminal carbon. So in this case, with the 2 carbons and the attached acid group, this would be ethanoic acid. Or with 4 carbons, this would be a butanoic acid.